Oh, wait till you're done here and you get endless emails of, hey, hey, alumnus, do you want to give us money?
Oh, yeah, I get those for half. They just keep trying to send me with like new links, like new ways to text me because I get stopped every time. And then I get another text from like a different alumni. I'm like, how are you still texting me?
Yep, let's have some fun with this. Let's have some fun with this. All right. So we talked about energy being stored as being what? He-Man says it all the time.
Power.
Power. Thank you for knowing who He-Man is.
I don't know who that is, but I saw it.
Really? Well, they're coming out with a new Masters of the Universe movie, so go watch it.
Why is he not wearing any clothes?
Because he's ripped. Because he's He-Man.
Looks like I'm gonna wear the gym again.
As you should. Oh, you're not going, never mind.
We know this equals potential. Times I, and our potential in this case is going to be our EMF. And so for an inductor, so we're actually going to have to go through some of the derivatives to make this actually make sense. Now, this is the EMF that's internal to the inductor. We need an external EMF to push power into the inductor. So how does the external EMF and the internal EMF equal, like, they're inverses, yeah. All right, so now we know we have so we just plug in that expression for the EMF into our equation from the top. We just took this and it went right in there. Okay. Now we do the thing that drives math professors absolutely up the wall. We now turn this into, oopsies. We don't have a new math professor. Oh no. Ah.
I didn't bring my son.
We went over that, right?
No, then I woke up, I'm like, damn.
How'd I do that? Kind of. This is something that every math professor would go derivatives are not fractions. I don't care. I can multiply through by dt and get rid of it. Yeah, I just multiplied through. So what do you remember? What is the difference? So if we integrate over dw, what is it? What does that equal? Who remembers? Okay, fine. What if we sum together all of the delta w's? You have the memory of a goldfish. You swim to this. You swim a circle in the bowl, and it's a new bowl. stored, it's energy, it's internal, stored internal energy. So that means on this side, even though it doesn't look like it, it's very, very, very simple integrals. So we are using so we have an identity, the power rule for integrals. And yeah, normally there would be an integration constant there, but we don't need to worry about that right now because we have limits. So well, I'm going to move this actually. Because inductance is a constant, you need to pull that out front. And you notice here that our exponent on the I is going to be 1. So if I use my formula here, I end up with L. So 1 over 1 plus 1 is 1/2. And then I prime, n plus 1, so 1 plus 1 is 2. And then I evaluate from 0 to current I. And we remember that evaluating the limits is a difference. So that's going to be 1/2 L I squared minus 0. So the energy stored in an inductor (1/2 Li squared). Here's a fun one: magnetic energy density. Those are 3 words you probably never wanted to see together. What? You're going to have to keep up. Did you not see the little, did you not see my little warning on Canvas? Did you not see the little video I put on there? Oh, no, click the link. That's that was your warning. Okay, magnetic energy density. Why would I put a scam on Canvas? No. Okay, energy density. Uh-huh. Yeah, that's your warning for the rest of the semester. But no, watch the video, it's worth it. Top of Canvas page. So, an energy density. That's energy, so it's energy per watt, per unit watt. Energy density, energy per unit watt. Yeah, per unit volume. So the volume we're thinking about Well, that's a horrible cylinder. But the volume we're thinking about, so there's our cross-sectional area. So this is our inductor with multiple turns. So the inductor, like you coil that wire, essentially you get a cylinder just with a lot of wire turns. Okay. What happened? Done it. Not as exciting as you think. Oh no, I mean literally around the world. What? Epcot is not for poor people. Oh, yeah. Oh,
Yeah, guys, I'm broke.
oh no, I was broke too. I got a scholarship to do it, but
Break?
no. Nope. Yep, they do. You just have to find the International Studies office and ask them how you do it. I thought we did. We have an international studies program. Now,
They want to keep us here.
you remember from a couple days ago, we have a definition of inductance. No, I is current.
B is equal to U N I over.
Yeah, and then we ended up with this. So your N over L becomes your little n. A zero. That is your permittivity of free space of a magnetic field. Permittivity of a vacuum now. I changed the terms in the textbooks. So since we have we can now plug in this for this term for inductance. But what is our expression for volume? What is our expression for volume? This is a cylinder, essentially. Now velocity, volume. Kind of.
One cylinders.
Pi r squared L. Okay, so and so our energy density for our inductor is going to be the stored energy over that volume pi r squared L, and that's going to equal 1/2 u0 n squared I squared. But I also remember that we had a law that told us the magnetic field is mu zero in I. I'm close to that. I have mu zero n squared I squared. So now I'm going to use a little trick. And I'm going to say, I'm going to multiply by 1, mu 0 over mu 0. So our magnetic energy density now we found this out for a solenoid. However, this does apply to all magnetic fields. All righty. So let's see. Now we have the current in an inductor increases from 0 to 2 amps during a time interval of 4 seconds. The inductor is a solenoid with radius 2 centimeters, length 12 centimeters, 9,000 turns. Calculate the average rate at which energy is stored in the inductor during this time interval. Okay, so stored energy, power. So this time we're going to go with the discrete forms. And so we know that that's also going to be delta U over delta T. What units will we be getting at the end of this? How do we know it's power? Yes, or V. Okay, fine. The old lady on the what? Yeah, or you notice it's energy over time, joules per second. We're just using a lot of W's, so. Okay, so we know that our delta U is going to be 1/2 L. Okay, so our delta U okay. So what we're going to end up with is 1/2 times the inductance and we end up getting a rate change for the current. So what this is going to turn into is 1/2 L I for the 2 amps squared over T 4 seconds minus 1/2 L I for 0 amps squared over, let's see, T0, which is 0. So this whole side here disappears. And we end up with 1/2 L oh, so that'll be 1/2. Okay, so let's start thinking about what else we could put in here. So L Now we're going to use Liam's definition. 1/2 mu 0 n squared A over L I squared over T. And we ended up with a combined equation of mu 0 n squared pi r squared. Where'd the pi r squared come from? The area. And here's where we could plug in numbers. Your mu 0 is going to be 4 pi times 10 -7th Tesla meters over amps. 9,000 turns squared times pi. Your radius is 0.02 meters squared, and your current 2 amps squared. Then you have 0.12 meters for your length, and your time is 4 seconds. Your power should come out to be about 0.533 watts. But I figured just going through magnetics was enough, so it's like, well, let's not take an exam over magnetics. Honestly, in the whole year of physics, magnetics is probably the worst part because the math is at the top of the level, and trying to envision it, trying to imagine these magnetic fields and what they're doing and the magnetic reactions, it's not very intuitive. Like keep repeating Lenz's law to yourself and try to envision it. Mm-hmm. Yep. I can make more. So we have to end with circuits that are combinations of resistors and inductors. So of course you see your little coil up there, that's your symbol for your inductor. And just as we did with capacitance, inductors will, you could say, charge over a period of time, but they'll grow to their maximum current over a given period of time. Because again, a current initially hits an inductor, and here we go with Lenz's law again. That current causes the magnetic field in the inductor. That growing current in the inductor causes a magnetic flux, a changing magnetic field. So now you have a changing magnetic field. This flux then causes a back current in the inductor because it needs a magnetic field that will it's going to need a back EMF to fight against the change in the flux or the flux of the magnetic field, the change in the magnetic field. So it's just Lenz's law is one of the hardest things to actually envision. And so with the current you're putting in fighting against the back EMF, that's why it takes a certain amount of time to get to the maximum current. Here's your little graph, what you're looking at. Current will grow over time. Voltage across the inductor will decrease over time. And now the fun begins. Okay, so let's draw an RL circuit. There's your resistor. There's your inductor. And then down here, we're gonna have our battery. Okay. And so that's going to make current go around this way. Let's see there. So this is L, that's your inductor. And so what I'm going to do is I'm going to bring back my old Russian friend. And I'm going to go around the circuit the same way as the current. So we remember now that we need the sum of our individual voltages, the delta V of the battery, delta V of the inductor, delta V of the resistor, that all equals 0. Okay, going across the battery that way, what do I put in for that delta V? Positive what? The battery. Yeah, it's positive, but positive what? Yeah, what do we call the voltage in the battery? Yep, the EMF. Now I'm going to actually designate this the EMF of the battery. You'll see why later. Okay. Let's see. Now the inductor, we go across the inductor in the direction of current. If we're going into the direction of current, what sign do we get? Negative. So negative in our voltage, remember, is going to be L okay. And then our resistor minus IR equals 0. Now we're going to rearrange things and we're going to get, let's see, L dIdt going to be the EMF of the battery minus IR. Now I want to separate variables. So I'm going to bring over the I prime, and then 1 over L dt. And now I can integrate it. I'm going to show you how to do this integral. I don't expect you to remember. I expect you to remember it because Gregory's taught you how to do it. But this is not one of the more simple ones. This is kind of like a next level one. So I'll show you how it works, but I don't expect you to really remember it. I just, maybe in the future, if you ever see it again, you'll have an idea of how it works. Because this side is going to go 0 to maximum current I. That side is going to go 0 to T, 1 over L. So the right side, as usual, is pretty simple because the 1 over L is a constant, and the integral of the differential just gives us back T. And then we evaluate T and 0. Now these are your regular ones. We don't do too many integrals with the partials. Now we do integrals with deltas, but those are imperfect derivatives, and that's a whole another thing. So the way we have to solve this is through a fun little thing called U substitution. Okay, so we're going to call our U so now if I take my derivative with respect to I, that's going to be dE dI minus because of course derivatives distribute. Now that first one, can anyone tell me what that first derivative becomes? If I differentiate a constant with respect to any variable, it becomes what? 0. Your equation you're taking the derivative of has to have the variable in it you're differentiating by in order to not be 0. If it does not have that variable in it, then the whole thing's 0. So then our derivative with respect to I, so we have I times R. So it's like your derivative with respect to x of x is just 1. You can look at it this way if you want to. So we have 0 minus what does that dI over dI become? 1. So in general, my du dI becomes negative R. And so then you notice in the integral, I have a dI that I have to replace. So I'm going to split this apart. Du is negative R dI. And then dI is going to be a negative 1 over R du. And so that's our replacement. Okay, now this becomes a lot easier. So the negative 1 over R, I'm just working on this one. The negative 1 over R pulls out front because it is a constant. I'm going to leave my indices because I'm going to replace U. You could go through a whole process of changing your limits, but I don't like to. So now what we have 1 over U du. And this we've seen before. This one is just a this is probably the integral I'd expect biologists to remember the most because you have to memorize it. Yep, so the integral of 1 over x dx is the natural log of x. It's just, so we have negative 1 over R ln of U evaluated at the limits. And so what we're going to do is we're going to bring this part of our equation back down, and we're going to replace U and bring this down. That integral is easy because the integral of a differential just gives us back t. So we're going to have 1 over L t 0 to t. Okay, so this left side, we're going to have our negative 1 over R. I have the natural log of E minus IR. Well, let's and we need to evaluate this at the limits. So that's going to be the natural log minus, so and again, I just plug in my limits and take the difference. Minus the natural log And then this right side is 1 over L t minus 0. Oh, hang on. Now look at the inside of those brackets. This one you should be able to do. Make that a single logarithm. Log of x minus log of y becomes what? Close. Close. Nope. You're closer with xy. They divide. It's log of x over y.
Oh.
Uh-huh. So minus 1 over r. Natural log. And our x is our e minus ir. Our y is just our eb t over l. Gonna move that 1 over r to the other side. All right. Now we can see what I'm trying to do is solve for current, but current is now buried inside of a natural log. Yep, I got to exponentiate. All right, and we know exponentiating a natural log gives us what's inside the natural log. All righty. Now I'm going to multiply through by my EMF. All right. Let's see, then minus IR. I'm going to change my signs. I'm going to factor out. What's left after I factor out the EMF? So 1 minus E RT over L, and then I'm going to divide through by R. And so this is your charging formula for your inductor in your circuit.
Yeah, that's it. You all back this thing. Like, the inductor and slowly running the circuit.
Yep. Because it makes you grow and it's fun for me. Now, we also know that by the time that the current in the inductor yields a voltage that is equal to the EMF, when the EMF of the battery is uninterrupted flowing through the inductor, that's going to be our maximum or our final current. Okay, and so we see that our final current is going to be EB over R. So another way to look at this is your current at any time t is going to be your final current all right, and your textbook has a thing called a charging time, a timing constant, and that is going to be L over R. The reason this is important is, like, say when t equals the timing constant, your inductor has been technically 63.2% charged. And if you're discharging the inductor, when t equals your timing constant, you will have 36.8% of your initial, well, it's IF. So because you're going backwards. So you'll have 36.8% of that maximum current left when you're discharging when t equals your timing constant. Okay, so these are two equations for solving the timing of an RL circuit. Okay, EMF as a function of time. Well, we know our EMF of our inductor is L di dt. And we have the equation we just came up with. So the I dt has to be the time derivative and so we'll start there and solve this on Monday and then continue into optics. Because we want to know how our voltage in this circuit changes as a function of time.
Oh.